Good day to everyone. So today I'm going to discuss about the Euler-Lagrange equation, and the same. The name is so daunting as you can hear it. It sounds so alien, but it will get more interesting as I go. As we go over. So before going to the Euler-Lagrange equation, let me give you a little background on Lagrange's equation. Well, Lagrange was 19 years old when he first worked on the torticollinear problem, thus giving birth to a new equation called Lagrange equation, as he was the one who discovered it. So he came up with it using his analysis on motion, classical mechanics, and also with the help of D'Alembert's principle. The torticollinear problem was first introduced by Galileo. As we all know, Galileo is the father of modern astronomy and modern sciences. Okay, that's enough for the Lagrange's background. So let me show you the Lagrange equation. So L is equal to P minus V. Lagrange's equation is just the difference between the kinetic energy and potential energy. Now, the kinetic energy here is E. And we all know that the formula for kinetic energy is 1/2 of mv squared. And for the potential energy, which is V here, is equal to mgy. Okay, this is the Lagrange equation of motion. And Lagrange equation of motion approaches the same answer with Newton's law of motion. And even though it just looks like this, there is a process on how to use this type of equation. Now, Euler came up with a new systematic approach of this equation to be used in further topics, including electromagnetics and especially classical mechanics. And there is also this equation that involves gravity. It is a combination of Lagrange equation, Euler-Lagrange equation to be exact, with gravity on its whole equation, but we're not gonna talk about it. So, let me introduce you to the Euler-Lagrange equation. Okay, this is partial of L, partial of theta, minus d over dt, times the partial of L with respect to partial of theta dot, which is equal to 0. Now, this is the Euler-Lagrange equation, which was also coined as a scientific poem in the physics community. And also, this is beautifully and elegantly made, as you can see here. It's so beautiful that I myself too calls it the most beautiful equation in physics. Okay, this is the Euler-Lagrange equation. Some calls it Euler, but it's not Euler. It's called as Euler-Lagrange equation. Okay? Euler-Lagrange equation. Okay? Now, let me give you a simple problem so for you to understand more about this equation. This simple problem is the most common problem when it comes to introducing Euler-Lagrange equation. Okay, suppose we have a pendulum here. I like this problem. There are two types of this problem. A pendulum that is suspended on another pendulum, but on this topic we are going to discuss about this on a single pendulum or simple pendulum. Okay, and we all know that if a pendulum stays at rest, it stays in the middle. So we can write this broken line here. And if a pendulum moves from left to right or back and forth, here like this, as you can see on the jeepney that you used to ride when you go to school, especially when it's raining, and you can see it on its wiper, it moves like this, back and forth. And when a pendulum moves back and forth, it creates an angle theta here. Okay? Now, the next thing we're going to do in this problem is you need to find the x and y values. And in order to find that, you need to recall the Cartesian coordinate or the x and y coordinates. Okay? This is the x and y coordinates here, and this is the y coordinates or y coordinate here. Okay? Can you imagine that? Okay? And in order to get these values, x values, we need to use the sine and cosine identities or functions in trigonometry. So sine of theta, which is equal to the opposite over the hypotenuse, which is the opposite is x, and the hypotenuse is L. I forgot to put L here, which is the length of the string. So we get cosine of theta is equal to x over L. Now, we can get the value of x by writing the equation, which is equal to L of, this is not cosine. So, what did I said earlier? So, this is sine. Sine of the opposite over the hypotenuse, sorry. So, we get L of sine of theta. Okay, L sine of theta by writing it here. And also, we can find the y by using cosine of theta. Now, cosine of theta is equal to the adjacent y over the hypotenuse L. So, I will replace this y. Okay, cosine of theta. So, we get the value of y by also doing the same process. So, y is equal to L of sine of theta. L of cosine of theta. Why do I mess up? Cosine of theta. Okay. Now, next step is getting the x dot, or the first derivative of x. And we all know in higher classical physics, especially on this subject that I'm on right now, x dot is equal to velocity. So, let me write it here. X dot is equal to velocity. Always remember that x dot or y dot or z dot is equal to velocity. Okay? You can encounter that if you want to proceed in higher physics. So, x dot is equal to velocity. Always remember that. So, x dot is the first derivative of this value here. So, L, first derivative of sine theta, is cosine of theta. And the first derivative of theta is theta dot. And then y dot. L, first derivative of cosine theta is minus sine theta. Okay? And theta dot. Now, we have two values here. And we can proceed to the Lagrange equation first using the kinetic energy. So, 1/2 mv squared. And since we have two values of velocity here, we can rewrite the equation as 1/2 of m of x dot plus y dot squared. And you can distribute squared inside. Okay, so we can rewrite that again for the second time. 1/2 of m of x dot squared plus y dot squared. Now, let me erase that. Okay, I'll just leave it there. So 1/2 m of mx dot squared, by rewriting that, we get 1/2 of m. So the value of x dot is L of cosine theta dot, plus negative of L of sine of theta dot. And don't forget that they are squared, so we can square L cosine theta dot, L sine and theta dot. Okay? So we can factor out the constants, or 1/2 of ml squared theta dot squared, and what we're left with inside. And always remember that positive times negative is equal to positive. So we're left with cosine squared theta plus sine squared theta. Okay, and we all know that in trigonometry, this identity is equal to 1. And if you don't believe me, you can search it on Google. But all I know is that this is 1. And since it is 1, it won't affect the whole value or the whole answer for kinetic energy. So we can just remove that. We can just neglect it because it's just equal to 1. So we have the answer for kinetic energy here, and we're not yet finished. We need to find the potential energy. Okay, let me move this whiteboard. So potential energy is equal to V, which is equal to mgL. Now, why did I put L here? Because on the free body diagram, we are suspended with the length of string. So I replace Y with L. Now, next step is plugging in the value of this one to here. We get mg L minus L of cosine of theta. Okay? Now, by putting out L, mgL of 1 minus cosine of theta. Okay, this is the answer for the potential energy. So, let me just write it at the top. Let me erase this. Okay? And now, since we have the kinetic and potential energy, we can now proceed to the Euler-Lagrange equation. Let me just write these two answers at the top so I won't forget it. I have a bad memory. I mean bad. I'm bad at remembering things. So mg of L of 1 minus cosine of theta. Or yeah, cosine theta. Now they're here. Now proceeding to the Euler-Lagrange equation. This requires a intermediate background in mathematics, but I'm sure you can easily understand it here that partial of L over partial of theta minus d dt times partial of L over partial of theta dot, which is equal to 0. Now, we need to look for an answer here that is a function with a partial of theta or dependent on the function of theta. Now, we can see that potential energy here has 1 minus cosine theta. Thus, we can get the partial of it. So, by getting its partial, we get mgl of sine of theta. Now, why is that? Why did it become sine from 1 minus cosine theta? We must recall in trigonometric identities that 1 minus cosine theta is just equal to sine of theta. Now you know the importance of trigonometric identities here. So, next step is first derivative with respect to time of partial of L over partial of theta dot. Now, we all know that kinetic energy has a function of theta dot squared. So, we can get its partial derivative, which is equal to ml squared of theta double dot, which is equal to 0. Now, as you can see here, we can cancel m, we can cancel L. Okay, now we're left with g sine of theta, which is equal to L of theta double dot. Now, in order to get the function of theta double dot, which is the missing piece of the jigsaw puzzle, we can rewrite it. So theta double dot is equal to g over L of sine of theta. Now we have the solution to this certain type of problem. I hope you understand what I did here, and also this just requires an intermediate background in mathematics, and I know you can understand it because some of it are being taught in high school. So that's it. Thank you.